Oh, did they not show up?
I don't know. I checked maybe a few days ago and they weren't there. So maybe, I don't know.
Let me see. I put some up recently.
Yeah, that area perimeter one is the 13th.
So you're not seeing the one from the 20th?
All right, let me go look. I mean, the last time I looked, which was maybe, at the beginning of the week.
Yeah, I started to update some more. I still need March 6th, but let me know if that's not showing up for you. Yeah.
Yes, yeah. You got the 20th and I see the 20th
Oh, it
is
looks like
up.
I didn't change the dates for any of them. I just copy pasted. So, yeah, I will keep getting them up. If I think I'm missing one in here, and then today's will be coming up. So I'll get those uploaded.
Okay. I was just wondering.
Yeah. All right. Hello, everyone, and welcome to MATHurdays. Math's so fun. We do it on Saturdays. My name's Teresa Wills, and I see we have a whole lot of returning folks. Welcome back. Today, we are going to play around with the Pythagorean theorem, but in ways that you've never really used it before, because typically the Pythagorean theorem is taught in middle or high school, and it's all about right triangles. But this time around, I want to look at things that are not right triangles and other ways that we could use it. So we're going to be thinking like mathematicians today, and really excited for this one. Let's go ahead and start off on slide 3 or 4. Share with us your successes and celebrations. What's going on in your world? I'm going to put gardening down for me. I'm trying to get outside as much as I can. And Raha, what are you doing for yourself for spring break?
Good afternoon, Teresa. I think I've already kind of started. I've woken up early and already napped today, so my attentions are taking naps, and that's it.
I hear ya. And Laura, it looks like you're in a similar boat. How's it going? Whoops, there's my microphone button. Yeah, I definitely can relate to you. Laura, it looks like you're in a similar boat. How's it going over on your end?
Good morning, or buenas tardes, or I don't even know what time it is, Teresa, but hi, guys. So it's been really nice. This is our second week of concurrent learning I teach in Fairfax County in Virginia. And it's been so nice. Like, I have loved every second of having my kids back, but I have basically come home and collapsed every night this week, and I feel like that's why I need spring break.
I hear you. On slide 3. Oh, and welcome. If you're just joining us, here is our slide deck. Join us down on slide 3 or 4. Somebody actually noticed, yeah, it's been 1 year since I started this whole MATHurdays stuff. It's kind of exciting to realize that, people are still interested in having this community and learning together, and it makes my heart smile. Let's see who wrote on slide 4. Someone else is on spring break and doing lots of walks. When you say walks, like, how far do you go? Do you do something fun while you're walking? Like, I will go anywhere that there's a Pokemon stop because I play Pokemon Go like a lot. How about you?
I'm up in Lexington. It's Karina, and I'm up in Lexington, Michigan at Camp Cavell. And the weather hopefully will turn. And I just walk on the beach and pick up beach glass and Petoskey with my dog.
Oh, that sounds just lovely.
And I'm also dog sitting for my friend's old dog while she's on vacation. Well, her and her boyfriend are on vacation, so I'm just kind of settling into that, getting used to her routine. And she's old and kind of, on her last years probably. So it's just kind of getting used to her. But yeah, thank God I'm able to come up here and walk the beach.
That sounds just lovely. I love finding beach class.
You need to recuperate after teaching and stuff and all the changes that have been going on. Mm-hmm. Can't imagine how hard it is for the kids if we're having a hard time too. So,
yeah. Well, welcome everyone. I see that there's some new folks coming in. If you need the link for today, it's in the chat box. Just click on that. I'm also projecting my slides here. Our routine today is Would You Rather? And you can join me down on slide 6 if it turns out we need more room. We have slide 7, but I think we've got a nice small group today. So down on slide 6, the question is, and if you saw my Twitter earlier today, I've been really into Reese's peanut butter cups recently. The question is, would you rather have 2 Reese's Minis or 1 Reese's Cup regular sized? If you want the 2, please put your response in the mint colored pieces. If you would rather have the 1, put it in the orange colored pieces. All right, we're seeing a definite ratio thing happening here. Let's see, if I put this bright blue around it, I'd love to hear from you. That's just kind of a heads up that I'm going to call on you. And I'm curious what you know about ratio of peanut butter to chocolate. So if that's you there in the blue, tell us what you're thinking.
Hi, Teresa. It's me, Raha. So I enjoy peanut butter, but I didn't grow up with it as much. Bangladesh, it's not very popular, but it's pretty good. So for me, when I think about the smaller Reese's, the ratio, how much chocolate is covered around the peanut butter is much comfortable for me versus the bigger one has a lot more peanut butter in the center. So like, I don't know the surface area of the smaller one, but the ratio of the inside versus the outside is perfect.
Ah, nice use of ratio. How about over here on the orange side? Now, it seems like you have a very similar reasoning. If that's what blue one was you, go ahead and tell us what you're thinking.
Yeah, that was me. It's Jennifer. Now, same idea, same principle, but for me, the larger one, the peanut butter is more spread out as opposed to compact in the smaller one. So I like the idea that there might be more peanut butter, but it's not all chunked together like in the small, the mini ones.
Oh, so it's almost like the bite is different.
Correct.
Oh.
I was just thinking that when Jennifer said it, I was like, it's the bite. When I take a bite of the smaller one, I can get equal-ish amounts of chocolate and peanut butter. I should have added that.
Huh. Somebody is using the term volume over here. If this was you, can you tell us, like, what does volume mean in terms of this type of a problem?
So I was thinking that the size of the one is more than twice the size of the 2 small.
Neat. And then my next question is, like, how could we prove that, right?
Right. Well, and if you're looking at the pictures there, it looks like even the diameter of the large one is more than twice the 2 diameters next to each other on the small. And of course, we even need to go for area, and that's going to make it even bigger.
Ah, cool. And how about down here we have the term cross section. What does that mean, and how could that help us determine which one we'd like?
Yeah, so my thought was as you're biting into it, each slice in terms of like just like a slightly bigger bite than you already have is kind of a good way of thinking of a cross section, you know, like a plainer cut. And if you look at the ratio, you're going to have a lot more of the peanut butter to the chocolate. And the one above that I was also talking about how when I find fun size candies tend to be just sort of an inferior product. I think that's also part of why, because people prefer that more satisfying bite.
So what I really like about this one today is, like, let's be honest, this is real important mathematics. Like when it comes down to it, we have a strong opinion about this. But what also comes out of it is so many great vocabulary terms. I feel really ready for a geometry unit where I'm going to be talking about ratios in terms of things like similar figures. And so Raha mentioned ratio early on. I'm going to make sure Raha is available to explain that definition to other kids in the class at any time that comes up. I saw Dan had the idea of cross section, and that's going to come up in our geometry unit. Gail over here was mentioning volume. And so in this activity, I actually gathered a lot of vocabulary terms. I asked you to rephrase it, and the purpose of it is so that throughout the rest of the unit, I have people I can call on to remind us of the vocabulary term instead of me being the one that does that. Cool. So we are going to come back to this at the very end of our session today. So I'm going to actually move this down to the very bottom so that I remember to come back to it. And I did find some other slides on Google. Slides 7 and 8 are just here. They have nothing to do with today's lesson other than I thought that you all might like them and could make really cool lessons with them. So those are just some screenshots that I found in finding this. And of course, you could make the would you rather quite different based on those. So if anyone has any ways of using it, go ahead and tweet that out also. But let's go ahead and jump right into our rich task. I have quite a fun one for us to explore today. And slide 10 has the link or has the problem solving oath. So what you're going to do is read this to yourself, put your name in the blank, and if you choose to pledge it, put your name in the chat box. I, Teresa, promise to try my best. I will make sense of patterns and numbers. I will use manipulatives and drawings. I will make mistakes. I will ask questions. I will listen to other ideas. I will stay engaged by always trying to find another solution or representation. I am a problem solver. I make the world a better place. And I think we have almost a couple more people. If you want to make that pledge, put your name in the chat box. We got a lot already. And our problem is on slide 11. So this is a problem that came out of a book from 5000 BC. And it's an experiment that, let me go ahead and highlight the line I'm going to read, says, suppose there were 3 squares made of beaten gold, and you were offered the one large large square, or 2 small squares. Which option would you choose? And we're going to explore this today with an app within GeoGebra. And what you're going to do is you're going to be thinking like mathematicians. So instead of trying to solve some like grand problem, instead you're going to play around with an applet and see if you can make some discoveries. And the way that we're going to do that, the link to the applet is below, but you're going to, on your group slides, have a sandbox. It's literally places for you to put screenshots, maybe some tables of ideas you're working on, with no clear direction other than you're noticing and you're wondering. If you think you've made some amazing discovery, on the slide below your sandbox, in this case 13, there's a place for you to write your theorem out. The length of 2 smaller sides must sum to a larger number than the length of the largest side to make a triangle. And I've got a screenshot of like 2 different examples, and I have a screenshot of a non-example. So in each of your group slides, you're going to have just that. You're going to have a sandbox. You can make as many copies as you want. You can have lots of sandboxes. And whenever you think you and your group found this cool theorem, you're going to display it on one of those theorem slides. So again, this one is geared a little bit more for middle high school, but the theorems that you might find can be relatable to all grade levels. That's the directions. If you are in a group with other people that have questions, please support them. And I'm going to go ahead and create them now. Alrighty, here are our breakout rooms. So the nice thing is if you are watching this from a distance, I can see each of my students working on the task. I can actually go into it and see exactly what they're doing. This is a new feature, I believe, of GeoGebra, where they are exploring this task. So I'm going to go in and just check out each room, see how people are doing.
It says under the
Yep.
group chat.
Yep, I see it.
Okay. Good morning.
Hi, everyone.
Morning.
Just checking in, seeing if you are able to open up that GeoGebra.
Yes, I got it.
Cool.
I got it.
See what we come up with.
Hi, everyone. I was just curious if you were able to open up that GeoGebra applet and start to play around in it.
Mine just opened.
Okay.
Yeah.
Algebra link so that I can, all right, so I just have to put my name and it'll sign me in. Perfect. All right, are you guys in the GeoGebra link as well?
Yeah.
Okay.
Yeah.
I've used it like with the protractor and for a couple of other things. I don't remember everything.
That's awesome.
All right, so
Hi, Naomi and Raha. I see that you're in here. I've got some pretty neat ways that I can kind of see the whole class working on this. But yeah, see what discoveries you can find. The red dot and the green dot do specific things, and the sliders at the bottom can change the sizes.
oh wait, so how do you make the sliders is what makes the squares get larger?
Mm-hmm.
Oh, I see. Okay.
I teach younger kids, so this math I haven't done in a while.
That's okay.
Hi, Karina. That makes you perfect for this activity.
Yep.
You know what happens is so often we memorize some rule, and instead this is going to have us kind of go back and be like, wait, what was that rule? How did it work? And so we're working like mathematicians work, where we don't necessarily have a destination, but we see what patterns we can notice.
Yeah, thank you.
Mm-hmm.
All right, 9, 9, and 4. That didn't work.
All right.
Hi, Group
wanna-
3. I see you already have your first image on here. What's some things you're starting to wonder?
I'm trying to figure out like if we increase the area of the the squares, does that affect the triangle that's formed in the middle?
Ooh, that is a really fun one to look at. Definitely encourage you to continue looking that up.
I mean, it connected for me.
Oh, you had two sides that were the same length?
Yes, I had 4 and 4, and they connected. I don't know if I did something wrong.
It looks like you did everything right. Yeah, you move it till it connects, but it won't snap. And that's because it's bound by geometry in this case.
Gotcha.
So does it turn black? Is that what happens? That's how you know it's snapped?
It doesn't snap.
Oh, so it doesn't matter that it turns black or not?
I don't see a black one. I'm gonna look.
Oh, I don't know, red, I don't know. It gets darker. The white circle gets darker. All right, I
Oh
don't
yeah,
know.
yeah, you're doing it right. Mm-hmm.
I don't know. Here's one. Let's see if this works. Take a look. Oopsie. Oh, shoot.
Side stuff.
All right, I gotta put it. All right, now I have to insert it over here, right? Wait 1 second. Okay, let me find my little thingy. Okay, here's it go.
Oh, that works.
I did this one. This took, so let me make it smaller.
Ah,
Oh, okay.
I
Yeah.
think those work.
Okay, mine was where is it? I got an 8, an 8, and a 5. I'm gonna take your number thingy, all right? Whoa, let's undo. I was gonna try to, all right, let me see if I can take your number thing. I did an 8
Go
and an 8,
for it.
5.
Go back and peek and see. Okay, so we need tables too.
Area of each square.
Gail, what are you thinking about with tables?
I don't have a table yet.
Oh, I thought I heard someone mention that you need tables.
Lisa said tables because I was back at the example. I see the table, and I'm terrible at making tables on this thing.
Okay.
Is there a table? Let me see. Undo. Let's go.
Technology. That's why it's spring break, and I'm only going to do fun stuff during spring break.
Or okay, that didn't work.
Ooh, I heard someone say something cool. That didn't work. What is it that you are trying to do that didn't work?
Well, there was over on the left next to the circles before I was able to click. Oh, now it's working again. That's so weird. I clicked on the number, and then below it there's like a place where you can an on-screen keyboard that you can type in. It has like X, Y, Z, pi. That's really weird. Now it works. That's weird.
Interesting.
Yeah, I did get it to work, but I was trying to, every number I put in,
That's weird.
every number I've put in, I haven't been able to get the points to overlap. So
Oh yeah, you have to drag the points. So these are just 4 squares out in space. But the interesting thing about it is that if you hold the green vertex, you can move the entire shape, and if you use the red vertex, you can rotate the shape.
yeah,
Oh, there it is.
I mean,
Okay.
I'm going by my understanding of Pythagorean theorem, and I was trying to avoid any Pythagorean triples.
Ah, that is really
And
clever.
so because I was trying to avoid them, I couldn't get my points to line up. But now I'm like, okay, let me just make sure it works. So now I fell back to a Pythagorean triple.
What if you made an equilateral triangle? Can you do that?
I am going to try that.
What would be
Yeah,
interesting?
I wanted to make sure for myself that it worked. So I fell back to what I knew. Okay, this is going to work because I know this is a right triangle. So now I'm going to branch back out because I was trying to avoid the right triangle.
Mm-hmm.
Well, I did a right triangle to get familiar with using the app. So I'm like, okay, I know 3, 4, and 5 will work. So here, let me see if I can get this into a triangle. So now that I know how to get that to work, I'm going to try other sides.
Right. All right, let's go there. Let's see, so blue can't be 3. 3.5. Nope.
Squares. So if we do plus medium and longest, then put the squares.
And do we also want to do, because I did notice on that example, she also talked about, there was one that was the perimeter of all 3. She chose area of yellow, area of red, and then the second table. This was just, for example, perimeter. Oh, yeah. Oh, that's a good idea. 81 square.
So then we can start looking at those numbers then. Okay. Now we need some more examples. Don't wait.
Okay.
I'm going back
And
to
Gail,
the
you're 12. You put my square. Put 144 for your 12.
Oh, I'm sorry.
All right, so I've got 4, 5, 6, and then I did 5, 6, 7, I think.
Oh, group. So it looks like you're finding some isosceles and scalene ones. What do those words mean?
If I remember correctly from geometry, I have fourth grade, we don't deal with it too much, but the size of if the size of the length of the triangle sides are equal or different.
Cool. Yeah, keep going with this. I bet you're going to find some really neat patterns and develop a theorem out of it.
Okay, so this is a 9.
Very clever, group. I see that you found isosceles and scalene, and that there's an observation that there's no equilateral. Is that because it's impossible to make? Is that just because you don't have one on here yet?
Oh, hold on.
Yeah, that's an equilateral one.
If I do 6 and 6, it did connect?
Oh, okay. We don't know. We were just hypothesizing that maybe you can't.
And that's exactly what mathematicians do. Yep.
So we're just hypothesizing.
So 6, 6,
What was
6,
I saying? I
6,
forgot
6.
this one. This was a
It
6.
does work. Teresa, I was trying to confirm if the triangle worked, but then I realized the Pythagorean theorem has to work with the right triangles. So I was like, oh, I can't use that.
So it's interesting that you say right triangle. In your
That's a 6.
table, which of those, like, what is a right triangle? Are they isosceles, scalene, or equilateral?
It would be scaling.
I think it could be isosceles. Yeah, it's usually
Oh,
scaling.
yes, it could be 45, 45, 90. Yes.
Right, it could be isosceles too, right. It's just not usually equilateral.
Right.
So sometimes people will
Like the 6,
actually,
4.
yeah,
do you do
some
that?
people might even change their table to talk about the triangle type in terms of the sides and the triangle type in terms of the angles. And you might see some interesting connections with those.
Ah, okay.
How'd you make that equilateral? I have a 6, 6, and 6, but mine's not
I
connecting.
have to move it around just a little bit in order for the dots to connect.
Yeah,
But
so
they're not a
Naomi, if you
rotation.
move your red dots, that'll move your whole figure and then you can kind of line them up.
Oh, I was wondering that.
Yeah.
Okay, that's what I was wondering, how you rotate it. Okay, that's what I was wondering. How do you rotate it? Oh,
Yeah,
all
so
right.
red
That's
moves, or red rotates, green moves, or I might have them backwards.
okay, gotcha now. All right, there we go. I see how you did the 6. I was wondering how you rotate it. That's what I was asking before. I guess I need to be clearer. So that means the 12, 12, and 12 should work then, right?
Try it.
Right.
I am. I'm using what I know to a new situation.
Hi, group. I love how you have 2 sets of numbers in your tables.
Thank you.
Oh, group one.
So I'll drop it right now. There it is. So this one would be right angle.
Hi, Laura. I noticed that you erased the word scaling there and put right angle there. Can you tell me why you did that?
Well, because I just duplicated the scaling tag from the other one. But we were trying to see if we could build a right angle triangle and make some observations about the sides, the area of the squares. And it's a right angle because it forms a 90-degree angle.
Interesting, but is it not scaling?
But you're right. It is also all the sides are not the same size. You're right about that.
So now you all are on this other kind of discovery area. Something can be right and scaling. So if it can be both, can other things be both? Can they be 3 things at a time? Can they be 4 things at a time?
Oh,
Question. So I could do 9,
So
3,
it's not like an 11.
7. Let's see. Oh, 5. Let me do.
Hi, group 2. I thought you all were about to make the golden ratio here when I started seeing the 2 boxes lined up with the other. So what is that a non-example of?
it's not an example of the triangle. So, non-example. Let's see, where should I write this? Beneath. Let me make that smaller. Non-example. Come on. I'm terrible with this stuff. Okay, space. Non-example. The sides of the red and blue squares are equal to the length of one side of the yellow. Let's see, I need to move this down some too, because the sides of the red and blue square, the sum, because it's the sum of the sides. Because the sum of the, Bruce, I have to tell you, this is what we did in class yesterday with my 8th graders, was make triangles and try to decide when you could make a triangle and when you couldn't.
Oh my gosh, how
The
fun.
triangle inequality.
No, and let me tell you, one of the boys in one class said, Miss Hudson, what about the Pythagorean theorem? And I was so shocked that I was like stunned for a minute, and then it hit me. Okay, he's talking about the hypotenuse being the longest side, and we used. I didn't get the kids out this year. We always use Exploragons, these are angle eggs, those little plastic sticks to build with, and we didn't use them this year, unfortunately. The kids love them when we do.
I find that my students forget about that triangle inequality once they start thinking about the Pythagorean theorem. And they totally forget that you can still make other triangles. They don't all have to be right triangles.
Right.
So
Because
I
that's
see
what
you
we
found an
focus-
obtuse one. That one's usually a little trickier to find. Like people usually find plenty of acute. We might even find a right, but that obtuse one, I wonder if there's something we could say about obtuse triangles.
I'm going to look at them. Let's see. Because I did one obtuse. No, Gail's was obtuse.
Yeah, it's in there. Oh, okay. So large
Well, we could
square
say that the
is
area
more
of
than the sum. I'm going for it.
Gal,
Of
the area
two
of
small
the
squares.
two small
There we go.
squares is larger than the area of the big one. Okay,
Yeah.
let me get back to what it was.
All right, folks, I'm going to ask you if you think that that is a true statement, the one that I'm putting in yellow here.
Right.
Can you give us some
Mhm.
examples and a non-example down on slide 22 so we can see that in multiple like visuals?
Okay.
Like just R squared is more than the sum. So you want us to find an obtuse, let's see, large square is more than the sum of the two smalls. Was that, let's see, 81, wait, 36, that was a 6, 9, and 12. That fit. And then isn't the acute going to be we've got two of those.
You are on a
Do
great
we have
track.
some acute
Keep rolling
triangles?
with it.
And it's also based on, whether the parents have opted in for hybrid or not.
Gotcha.
Because then you have kids who just always hybrid because that's what the parents have said.
Hi there, group.
Hi.
This is a neat discovery. If it is scaling with all odd numbers, it doesn't work. Can you tell me what doesn't work?
So we were just trying to play with odd numbers to see if they would connect. So when it's Naomi tried, I hope I said your name right, tried 11, 11, 11, and it was an equilateral with all odd numbers. The dots connected. Then I tried 5, 5, I think 9. So that's a isosceles with all odd numbers, and it worked. But then I tried with, right now I have 11, 3, and 5. So it's scaling with different odd numbers, and it didn't work. The sides don't connect.
Oh, I can't make this one move.
I'm trying to make sure that that's the case all the time.
Yeah, I love that.
Ooh, but if I do 5, 5, 13, it doesn't work either. So it has to do something with...
I did 13, 5. I did a 13, 11, and a 5, and it worked. I think it works.
Oh, you know why? Maybe because...
Oh, yeah, I got it.
My two smaller side, 5, 5. If I add 5 and 5, I get 10, which is less than 13.
Right.
So maybe if something about like the smaller sides, if I add them.
Hey, so wait a minute. So look, I got 5, 13, 11, and 5, and it worked. So I guess our hypothesis is not right. If it is scaling with all odds, it doesn't work. Because we found a case that does. Yeah, I'll put it in. You can take a look.
Yes, yeah.
Hi, group. I see your sandbox is looking just beautiful with so many different examples on here. And I'm curious, what are some things that you're starting to notice? What are some things you're starting to wonder?
Well, one thing Roanna had noticed was that we seem to be making like isosceles or scaling, but she had a wondering about like what it would look like if we tried equilateral, would be able to make an equilateral triangle and have it be a right angle at the same time, or what that would look like.
Very cool. So I see that you're naming your triangles by both angle measures and by lengths of their sides.
Yes.
All right, Roanna, there's the equilateral. I haven't, like, the equilateral, it just can't be a right angle.
Yes. But it would be an acute angle.
Yes, so equilateral and acute.
So can equilateral ever be right?
No. I don't.
And
I don't
Because
think
for
so.
right, one of the side has to be longer to not be a right angle.
Yeah, in order to accommodate the long side, like in order to have it be the right angle, you have to have that one long side.
Yes, and I feel with the scalene and the isosceles we could do, because one side was always long, which was managing to touch the two ends of the other squares.
So what you all are starting to discover is something that people will often do in a matrix. And I've got that on the next slide there. But I can never spell isosceles. I put it in here. If you think you found an example of an acute scalene, you can put that example right there in the matrix. And, the same for the others. It's harder than it looks to try and find examples of all of those. But if you think you've got them, feel free to work on that matrix and see if you can find all of those.
Yes.
All right, so I'm going to drop that because we already have acute and scalene.
Okay, and I'm going to try. Oh, well, let's see if this, that's 14. I think this worked. Yeah, there we go. Look, I have 5, 9, and 11.
Okay.
5, 9, and 11 backs up what we said too, right?
Oh, perfect. And 5, 9, 13 also works.
I'm just gonna put it inside there since that cell got so big. So what did I say? I
Yeah,
said
go for it. Please.
9, oopsie, 9 and 11. Okay.
So interesting.
Okay. Yeah, but well, this is 8th grade, so they have the background knowledge of isosceles and scalene and equilateral, so they can have this conversation.
Okay, we have 2 more minutes.
I was still gonna cut out. You kept me there.
Welcome back, everyone. Hi there. Welcome back to the main room. You know, so often in mathematics, we try to get a solution. We try to solve a problem. But one thing that is really great about mathematicians is that they don't always try to solve a problem. Sometimes they just explore things and see if there's relationships within them. And that's what I tried to do with you all. I did give you some guidance in what to explore, but it was hopefully a refreshing time for you just to explore neat things that happen with squares and triangles. And there's a couple of things that are really important that come out of this. And I would love to start off with group 3. They're on slide 23, and I'm also going to share my screen if you want to follow along and collaborate. But group 3 started with a whole bunch of these different triangles and squares, and they started to name them. And group 3, would you kind of walk us through your journey of naming these different situations?
Hi, Teresa. So in our group, we were thinking about, at first we were just thinking about the size of the length of the triangle side. So whether it was isosceles or scalene, but then you kind of pushed our thinking to think about the angle as well. If you look at the triangle, that's the area of the squares are 4, 8, and 7. It's a scalene triangle, but it's also a right angle triangle. So there's more than one way to identify or classify a triangle.
And then I know I was chatting with you all about slide 24, but what are you starting to discover? What questions were you getting to ask about slide 24?
So Ren and I were talking about how even just the creation of slide 24 and just having to come up with visuals for like what it would look like to be an acute and a scalene triangle, or what would be acute and isosceles. It really pushed our thinking to try to create those triangles. And it was, I think, to me, a more authentic way of like building that concept versus just memorizing like a definition. This is what an isosceles triangle is. This is what a scalene triangle is. Because even I was having to like go back into my memory of like middle school geometry of like, what is that definition? So having to fill out that matrix and create for myself what it would look like was a stronger way for me to visualize those triangles.
Mm-hmm. Can everyone else put a comment in the chat box? What does this matrix make you wonder? It can be very specific, it can be very broad, but put a wondering you have just looking at this matrix in the chat box. So there are several questions about these unfilled areas, which does lead us into a great activity next, like can we fill all of them? And then we get to these questions about like, does it work? And I've been into all of your groups and I keep asking you, what doesn't work? Like what does work? When you say work, what does that mean? And it's really neat to hear how even a group of 2 people working together might have different ideas of what their definition of working means. Let's take a look here at group 2. So group 3 really looked at classification by angles and sides, and group 3 is, group 2 is on slide 22. Let's come down to 22. And group 2, it looks like you were all about the obtuse triangles. And tell us what your discoveries were.
We started by putting together triangles, and we had a table that we started putting together up on slide 19, and we were listing the lengths of the sides and the squares of those lengths, and then we were looking at those numbers for the squares. So then we started seeing that, well, if we looked at the largest side and it was more than the two small sides added together, then it was an obtuse triangle.
So that is interesting. We are looking specifically at areas now, not just the lengths of the sides, but you're telling me that this area on side 22, got this bright red circle around it, this area here has a relationship to the other two?
Yeah, it's more than the other two added together.
So does that work? Can everyone confirm? Does that work on this one also? That 36 plus 81 is bigger than 144?
No, it's less than.
Oh, it's less than.
The longest side has to be more than the other two added.
And then if we do that, we're going to get an obtuse triangle.
Yes.
Let's take a look at group 1 on slide 16. They found another type of an always triangle. Group 1, tell us what you noticed.
Since I'm the one that did it, I'll talk about it. What was your question again, Teresa? Could you repeat it?
On slide 16, you have this theorem. Can you tell us what you've noticed?
I just basically, I was working with the right triangle, and I worked with the Pythagorean triples just because I knew it would work to be able to play with the triangles. And you came in and said, what about an equilateral triangle? And I went, interesting thought. So I started playing with the equilateral one, which has got the acute angles. And then I thought, played with an obtuse one and just started playing with the numbers and discovered that if I add the two sides, which we all know from the Pythagorean theorem of the smaller sides, they'll equal the larger side for the right triangle, but it doesn't work in an equilateral and obtuse. And while I've always known that in my own head, because somebody told me that, it gave me a chance with the tools to be able to actually visually explore it myself and find that out. And I hadn't quite taken it further to see that what you're showing right now and what other people have talked about, that when the angles are, when it's obtuse, it's going to be less than the third side, the longer side. But when it's acute, or when it's equilateral, it actually is an acute. It's going to be where the total adds up to more than the third side. So I enjoyed just having the opportunity to visually see something mathematically that I know works, or because I've been told it works. And that's why I'm really, as a teacher, I want to have my students do the visuals, because then it makes sense.
That was so beautifully stated. I would love for us to try to summarize this, because this is a really large concept. Typically, when we see the Pythagorean theorem, we will hear something like a squared plus b squared equals c squared. I just put that in the chat box. And this is all we remember from it. But really what we're trying to say is that works for right angles. But guess what? There are inequalities that work for acute angles, and there is an inequality statement that works for obtuse angles. If you see that today, if you would like to try and summarize that, what are other mathematical statements, inequalities that we could write that relate to the Pythagorean theorem? Feel free to put those in the chat box. And Raha, I saw that you are summarizing in the chat. Would you tell us what you were thinking about this?
So I tutor like up to high school, and the ideas of why Pythagorean theorem works, it's kind of like, this is how it works and this is how we're going to do it, but I never got to be a learner and explore it myself. I've watched multiple like videos of why it works, but I never got to actually explore it. So today I was able to play with different numbers and see, even if it's not a right triangle, they do connect and it might work. It might have to do with different sides, even, odd, and that's what Naomi and I kind of focused on, the number, the sides being odd and even, and whether it works or not. So it was pretty cool to be a learner. Well, it always is in your classroom, to learn and kind of visualize how these theorems come to life.
Yeah. So these theorems are so much bigger than what we typically, do in a math class. And I see that Gail is sending that out. But the Pythagorean theorem should really be looked at in all three of these ways that I'm putting in the chat box. So we can either have that C be less than, greater than, or equal to, and the triangle on the inside will either be acute, obtuse, or right. Now, in the initial question, when we were asking, like, would you rather have the two smaller squares of gold, or in our round case, the Reese's Peanut Butter Cup, or you would rather have the larger, we can use the Pythagorean theorem, but we don't have to be focused so much on the equals part. We can be also equally focused on the greater than and the less than, as that tells us some really interesting things about what we would rather have in terms of that Reese's Peanut Butter Cup. So there was a lot of big math ideas today. If you want to continue chatting these math ideas with me, I'd be more than happy to help get some kind of clarification happening in here. But at the same time, I know we are about at the end of our hour. I would like to invite you down to slide 38, because there is something really cool here. In our initial question, we were asking, would you rather have the big Reese's cup, or would you rather have the two small? And after doing this activity, you might be interested to know that the Pythagorean theorem also works on circles. It works on all sorts of different areas. And if you align them just so, you will find out the answer to your question of, would you rather have the two smaller, or would you rather have the larger candy? This is not as beautiful as GeoGebra is, but and you can use this to figure that out. So, anytime you're given those situations, you can ask yourself, hey, if it's right, perfect. I can choose either one. They're equal. But if they're obtuse or acute, there's a better answer. So I hope next time you do Pythagorean theorem, you think about it in terms of circles, and you think about it in terms of acute and obtuse triangles, because those might actually be more important than simply the right. All right, folks, I'm going to be happy to stay on if you all have any other questions. If you want to see other things, let me know in the virtual parking lot at the end. But I hope that this was fun for you. I hope you got a chance to be a mathematician again. You got to check out a new tool, in this case, GeoGebra, and that you had fun with it.
Now it's making me think of, like, as the ratio of the areas into the other area, and not necessarily, because the area of the squares is how we determined Pythagorean theorem. That's where the theorem comes from. So circles also have areas. So you're just taking half a circle and thinking about it. That's so cool.
Yeah, so you are taking half a circle, which makes this problem about the beaten pieces of gold. Who has square pieces of gold? I don't know about any of you all, but I don't. But I do have plenty of coins. And if those coins were actually made out of gold, I could use the Pythagorean theorem to determine if I would rather have two small coins or a large coin, assuming I was going to smelt it down.
So then, because gold is also measured in weight in a lot of different countries, would weight Tabitha?
Yes. So this is the debate that's happening on Twitter right now. Apparently, Reese's peanut butter cups are not cylinders. So this makes the problem a little trickier. They are a different shape. I don't remember what it is, but it starts with an F. And it's kind of conical, like a cone, but cut off. And so because of that, this gets altered a little bit. Oh, yeah, there it is. Lisa, how do you say that? A frustrum?
I don't know if it's frustrum or frustrum, maybe. I don't know.
I just learned it today.
I'm just guessing. I think that's it.
But these ones also have different heights, so you would have to consider that also. Yeah, and the width of it. So I see it as a trapezoid cross section through the greatest diameter. And if you think about the trapezoid formula, it finds an average of your top and your bottom. So I would imagine you'd do the same thing here.
Hey, I see this as a calculus problem.
Oh my gosh,
Teresa,
it's such a calculus problem.
With the Lisa's cups.
Okay, where are you going, Lisa, with this as the calculus problem?
Just because it's the average of all those different cross sections. I just remember calculus was such a frustration to me because I never could grasp it and understand it.
Yeah.
I do have a question for you. Back on the Pythagorean theorem, I have seen that done with the semicircles before, and it hit me one time. Is it because all the figures we have been using in the past have been similar shapes? So the semicircles would be similar shapes. And then I thought, well, how about using equilateral triangles? Those would all be similar shapes.
Yep, it works
Plug
for
an
triangles.
equilateral triangle along each side or something. So I don't know.
Yes, so it does work for any similar figure because they are bound. And the funny thing is Google Slides help us to see it. You can, if I click on it, oh, this isn't actually a circle. These are supposed to be semicircles, not ovals, but you can even see in the Google slide that it's bound by this square. And so the ratio of the area of the square to the area of the semicircle is going to be the same no matter which one I'm on. So it's as if they are still squares, but we're only looking at a small ratio of it. So that gets really, really fun. It does work for pentagons. Again, they all have to be similar because you can see the way that it's bound by that square. So every pentagon that I have, when I find the area of this one and I find the area of another similar, it's still going to be the same shaded inside of the square box. That ratio remains the same. Yeah, thanks for coming, and happy MATHurdays year. I guess we're a whole year in now. All right, folks, have a great rest of your day.